Okay. So I was going to talk about a cool application of the path integral where you can actually calculate something, and an example where using the regular Schrodinger equation would be much more complicated, which is the Aharonov-Bohm effect. And this is one of the more mysterious properties of quantum mechanics. And the setup is the following. Suppose you have here some coordinates, spatial coordinates. We're going to call them x1 and x2. And we're going to have a particle, like an electron, sitting over here at some initial position xi vector, at some x1 in the plane. And you just define some plane and the electron sits in it. And you imagine in this area you have a magnetic field pointing in the outward direction. And suppose this magnetic field is just completely isolated from everything. It's just a magnetic field confined to this area, this orange area. And other than it just sitting there and pointing out of the plane, it doesn't do anything. Like it's completely isolated. There's no way the electron or whatever, it doesn't feel it in any sense. It, doesn't apply a force to it, nothing. Just sits there out of the plane, is completely insulated from the outside. And what we'll see is there's still a quantum mechanical effect due to this magnetic field. And what we're going to do is the usual thing. We're going to calculate the propagator associated with moving the particle from the initial position here to some final position. And remember, the path integral tells you that the probability amplitude associated with propagating from that initial spot to the final spot depends on the paths, all possible paths that go between those 2 points. So it'll turn out that the path integral gives us a good way of understanding this problem that would otherwise be sort of tricky to deal with in other pictures, which I think you could. So what's the idea here is we need to figure out what the Lagrangian is. Remember, the path integral depends on the classical Lagrangian. And you just recall the form of the electromagnetic force on a charged particle. There's the charge, and then the velocity of the particle couples to the B field, and you also have the charge just coupling to any E field. So that's what it is. And of course, the Lagrangian is kinetic minus the potential. So we have to figure out what the appropriate potential to use. So we want to know what is the potential. Which, obviously has to satisfy that if we take minus its gradient, you get the force. So when you want to do that, when you want to create the potential associated with electromagnetic fields, you have to introduce the vector and scalar potential. I hope you guys have seen this at some point, but you introduce a vector potential which satisfies the following equation. that when you take its curl, it gives you the B field. And then you also have a scalar potential for which the E field is equal to minus the gradient of the scalar potential, and then also any explicit time dependence in the vector potential. And in that case, you can actually rewrite the force in terms of these potential functions. The force is going to be the charge. And now you have the part that comes from the E field, which is grad phi, minus partial t A vector. Then you have the stuff that comes from the B field, which is V cross curl of A. And now you can use some vector calculus identities, vector, curl identities to rewrite this as Q minus grad phi minus, I'm going to pull out an overall factor of a minus sign here, and you get partial A. And then this curl you can rewrite using an identity for a double curl, which says that this is equal to V dotted into the gradient. So it's the derivative along the V direction acting on A minus the gradient of V dot A. So that's just a vector identity. And what this guy is, this must be the full time derivative of A, because A can change via explicit changes in time, if it's explicitly time dependent, or it can change due to the particle motion. Because remember, V itself is the particle position, right? Differentiated with respect to time. So this is just like the chain rule. The full time derivative, the full time derivative is equal to partial t plus, dx dt dx vector. And of course, we always write d dx vector as the gradient. So that's just the gradient with respect to the coordinate x. So that's just the full full-time derivative of A. So this whole thing is Q minus grad phi minus dA dt, and then you have a plus gradient of V dot A. Okay, so that's a little bit more convenient expression, because now if we look at our situation here, we don't have any electric fields. So there's no scalar potential here. It doesn't contribute anything. So that part's zero. And as long as there are no accelerations of the particle and no additional generated magnetic fields, if the only one is the static magnetic field, then the vector potential also doesn't change in time, and so we can drop this term too. So in the end, for our problem, of a static magnetic field in that cylinder. This is just equal to the charge gradient of V dot A. And that's very convenient because now you can see explicitly that, right, the potential is equal to minus the charge, x dot now, and the velocity, dotted into A. I'll put little vectors here. So that's the potential that we need. And now we can write down our classical Lagrangian, right? Our classical Lagrangian is the kinetic energy, 1/2 mv squared. And then we have minus the potential, so it's plus q x dot dotted into A. And this is the Lagrangian that we have to work with for our problem. And so what's interesting is that, of course, we know that in the Feynman path integral, we have to integrate the Lagrangian, right, from the initial time to the final time. And so if we go from some initial position at some initial time to the final position at the final time, then the change due to this term, we can actually write that. The change due to the charge, so the action due to the charge, it's going to be Q integral from Ti to Tf of this part of the Lagrangian, which is x dot, and again, it's an integral over time. X dot is dx dt, dotted into A, right? But now we can use, we can just recognize that this is just dx dt, so we can change variables in the integration to just dx. And then, so this has to be equal to the integral from the initial position to the final position of dx dotted into A, where x is, the coordinate along the path that we're integrating over. So, we're again taking some path, right, in time, x of t. And so we're just changing variables in the integration, and you essentially, you can write that integral in terms of the integral along the path described by x as you go from the initial position to the final position. So that's what it has to be. And that'll turn out to actually have a contribution when we include the cylinder, which is surprising. But any questions about the setup? Okay, cool. So we're going to calculate the propagator for this thing using what we've derived now. So we want to know the propagator from moving from and let's just call it, I want to drop the little subscripts. Well, I know we can put the, so we want to go to some final, we want to know this propagator, right? So what we note, and we know we have to sum over all paths and going from the initial point to the final point. What we note is that we can break up the paths into ones that go on top of the cylinder and ones that go on the bottom. So I should say that, so I was a little bit, so this drawing is a little bit sloppy. As I said, the cylinder is impenetrable. So we can set up like infinite potential walls at the cylinder so that no path actually goes through it. So we can sort of, and then in that case, if we have sort of infinitely large potential walls at the cylinder surface, then the paths, all the paths that we integrate over, all these crazy ones, we can sort of break them up into two kinds of paths, right? Ones that go on top and ones that go on the bottom of the cylinder. Assuming the cylinder is just infinitely impenetrable, that it's got, completely like infinitely tall potential walls at the boundary of the cylinder, so that no paths going through the cylinder can contribute, because the potential will just kill that contribution in there. So this we can break up into paths above, which we now integrate over. And again, we have the exponential of the I over h bar of, the integral over time of the, the classic Lagrangian. And then we can also add all the ones below, and that'll give us all the possible paths. Each path is either above or below the cylinder. And that's going to be the first step. And so now what we do is we recognize that what kind of integration do we have here? We have in the action. So for the action, we know that one of the terms in the action will just be this guy. That's from the charge. Then we're also integrating this part, but this part is just the kinetic energy, and we already know how to do that. That comes from the free particle propagator, but we already derived that, so we can just use it. We can use the answer that we got for the free particle last time. And so we can start writing this out. So from the free particle portion, from the kinetic energy portion, we get the square root factor, where it's m over 2 pi I h bar, and now it's delta t. It's the time over which the particle moves from the initial point to the final point. And then we have the contributions from the two kinds of paths. And so what do we know? We know that for each one, there's going to be a factor as follows. There's going to be an exponential of IQ over h bar of the integral from the initial location to the final location of dx, right, dotted into A. And this is going to be over paths that go above the cylinder. And then there's going to be a contribution for the paths that go below the cylinder. But it also has the same form, that it's just IQ over h bar xi xf dx dot A. And the only thing that we're missing are any possible, is a phase factor that in principle could be different from the top to the bottom. And so that's what we'll try to determine, is any kind of, we'll try to determine. So the only other term that's left to include here is any phase, which I'm just going to denote as I theta b for bottom and theta t for top. Everything else just comes out from the free particle portion and what we just derived for the action for the charge part. And then the only difference between the top and bottom can only be in some kind of phase factor, which we're going to try to determine. And the overall phase, of course, of the propagator, that doesn't matter because we know that wave functions are only defined up to a phase. So we can factor out an overall phase. And what we get is we can factor out, say, the phase associated with going through the top paths. And what we're left with here, and we can also factor out, these themselves are phase factors, so we can also factor out one of these exponentials. We're going to factor out this one, the one that goes for the over top paths, the first one. So IQ over H bar, integral dx dot A. And I have to specify these somehow. So this is over the top paths and these are over the bottom ones. So we're going to extract this factor out. So this is all just a phase out in front. And then what you have left over is 1 plus e to the I delta theta, which delta theta is just the difference between theta b and theta t. It's the relative phase difference associated with the top and bottom paths. And just over H bar is convenient normalization. So then the theta here is in units of H bar. I guess you can define it without an H bar if you wanted, but it's convenient this way. And now here, what do we get? We get a difference in the two kinds of integrals because we're factoring out this integral over the top paths. So what we're left with is an integral from the initial point to the final point of integrations that go over paths below the cylinder minus the integration that goes over a path that's at the top of the cylinder. Over the top of the cylinder. Yeah, so you have that. So all I did was I just factored out an overall phase. And now the thing to notice is that this guy, I can rewrite it as a loop integration, because what is this? We have our cylinder here, B. This integration is over some path that goes along the bottom of the cylinder. So you integrate this way along this path. And then this guy minus, right, xi to xf, it's minus the integral of a path that goes along the top, right? And if you take a minus sign, that's like transversing the path backwards. So that's as if taking the path from the final location, this is xf, this is xi, final location, and going back to where you started. So in the end, you see the combination of these two things is a loop integral that encloses the cylinder. So this whole thing here, this is a loop integral that goes around the cylinder over some closed loop. And it's closed because the initial and final locations for both kinds of paths are the same. So it always makes a closed loop. It's a closed loop of dx dotted into A. And now you will have to remember your curl theorem, which says that an integral, a loop integral, or like Ampere's law or whatever, the loop integral of this vector is the same as the surface integral of the area that loop encloses, dotted into the curl of A. It's just the curl theorem from vector calculus. And that, of course, is nothing but the magnetic field, because remember, the vector potential, the curl of it just gives you the magnetic field. So this must be the surface integral. And this is the kind, if you have some loop, right, the surface element is just the area element that sort of points according to the right-hand rule. So if the loop is sort of being transversed this way, counterclockwise, then you use the right-hand rule, curl your fingers around the direction of the loop, and the surface element just points in that direction. So it points in the same direction as the field in the cylinder, and out of the plane. Here I wrote it kind of on its side, but hopefully you see what I'm trying to get at there. And this is just B. And what is this thing? This is nothing but the flux of the magnetic field. It's the magnitude of the magnetic field, right? Multiplied by that area. It's B0 times the area of the cylinder, because that's where the magnetic field lives. So the contribution to this area integral is going to be 0 everywhere except where the cylinder sits, and that's where we'll pick up the contribution. If we integrate over this, so it becomes essentially a surface integral, right, over this entire area, and the only part that picks up anything is where you have a magnetic field, because you're integrating B dot S. So this becomes the flux. So that's really quite interesting. It tells you that the flux inside the cylinder actually contributes to the relative phase difference between paths that go on top and bottom of the cylinder. It contributes to the propagator, and it will actually contribute to the actual probability. It's more than just an overall phase, because you see we factored out an overall phase here, and this term has 1 plus something. And when you take the square magnitude of this thing, you'll no longer just get like 1. So let me show you that. So we have this, and now if we take the magnitude of the propagator, oops. If we take the magnitude of the propagator squared, which would give us a sense of the probability of moving from one point to the other. Oh, sorry. Doing these backwards. So it's the propagator going position TF at time TF from TI. If we take this thing squared, what do we get? Well, okay, so I factored out this overall phase. This just gives me 1. So from the square root, I get an m over 2 pi h bar delta t, or delta t is just TF minus TI. The I doesn't do anything. It's just magnitude is 1. It's just also just contributes to the overall phase there. And what do we have left? Well, we have the magnitude squared of 1 plus e to the I delta theta over h bar, where delta theta is some possible phase difference between the top and bottom. We haven't specified what it is. You could go back to the sort of free particle solution, figure out in more detail what exactly it is. As remember, the free particle solution, they had this square root factor, but then it also had a phase related to sort of the classical path that the particle takes. Well, you can do the same thing here. It would be the phase associated with like the classical path that goes on top of the cylinder versus the bottom. It would be like some kind of piecewise linear thing where you try to keep the velocity constant, but such that it still kind of turns around and goes around the cylinder. Something like that. It's sort of, you can you can do the same thing we did before for the classical propagator for that phase factor, but I just don't want to do it because it's a little bit tedious. But you can imagine that there's a sort of classical, most likely classical path that kind of goes on the top and one that goes on the bottom. So you can actually do this a little bit more rigorously and calculate the free particle part by just expanding around what the most classical path would be that goes on the top or the bottom. And then you would just do the propagator for those two paths, which would look like, again, the square root and some phase. And I just didn't want to calculate out the phase. It will depend on, you know, it would look, if you just go back to, you know, last lecture, you see that we calculated for like a straight line path. It picked up some phase. So I just didn't want to, you can do it. You can put in those explicitly and like actually get, you know, a full blown propagator that has everything in it. But I'm just going to say, well, there's going to be some phase difference due to that phase difference in those two different kinds of classical paths. You expand around the ones that go on the top and the bottom. So I'm just going to call it delta theta because that's not the point. The point is what happens with the magnetic field. What does that do? And the point is that we just found that this whole thing actually contributes something to this this part. It contributes a factor. And what is it? It is I Q over H bar, and it's the flux, phi B. So that's really pretty interesting, right? Because now when we take the magnitude squared there, what do we get? Well, we get this stuff out here. And when you take the magnitude squared, well, you can expand this right into. It depends on how you want to do it. You could take the Euler's formula, right, and expand this into a cosine plus I sine, and then you take the sum, and you square each of those and add them together. But yeah, so but what you get is what you get is 2 plus 2 cosine of delta theta over H bar plus Q magnetic flux over H bar. And now you can use a half angle formula, I guess, yeah, to rewrite this as, oh, sorry, I guess this is, should be, let me think a little bit. So, yeah, you can just write this. So this is 1 plus e to the I alpha, and then we can multiply by its complex conjugate. So what you get is 1 plus 1 from the 2 cross terms, then you get plus e to the I alpha plus e to the minus I alpha, which is 2 plus 2 cosine alpha. So that's where that comes from. Okay, but now you can use half angle formula to rewrite this as 2m. So these 2's cancel, but then you get a factor of 2 from the half angle formula, pi h bar delta t, and it's cosine squared of delta theta plus q phi b over 2h bar. And what does it mean? It means that this actually has like real consequences for experimental measurements, right? The probability that you end up in some final location actually will depend on the magnetic flux. And what you can do, and sometimes I assign this as a homework problem, you can actually work all this out exactly for this kind of experiment, for instance. Say you have a two-slit problem, and you have your cylinder with the magnetic field, and then you have your screen. You can use this propagator and, calculating out these things more explicitly. You can then break up you can actually calculate what happens to the two-slit interference pattern. So if there's no field, we know that we get a two-slit interference pattern on the screen where the intensity of the so if you're shooting electrons through here, then they'll hit the screen with some probability that sort of gives you these interference fringes due to the two-slit interference. But what you can do is you can actually calculate the path integral propagator for going from sort of the top and the bottom like this from the two slits. You can assume these are closely spaced, so that's basically you can use the same propagator that we would derive that we derived for this situation. And you can calculate what happens to the two-slit interference. And basically what happens, like in this cosine squared, what will happen is the delta theta roughly tells you about the position you're at from the center line from the two slits. The delta theta is basically going to tell you the difference between classical paths that go on the top and bottom. So it'll depend on this delta theta, right? Because the ones that go on the top can go straight there, and the ones that go on the bottom of the cylinder have to do a detour. And so there will be a phase difference associated with just how far up you are on this screen. So that'll be delta theta. And if there's no magnetic field there, then from that, you could just calculate what the two-slit interference pattern is. You can use the path integral to calculate two-slit interference too, if you wanted. If there's no magnetic field at all, then you can calculate the contribution from these two paths from the two slits, and that will give you a two-slit interference, and the kind of phase difference between those two paths will depend on where you are on the screen. So you can sort of do that. So that's actually another common example problem, is calculating two-slit interference pattern using the path integral. But anyway, the point is, if you do that in the presence of this B field and you use this propagator, you'll notice that the delta theta, which would normally tell you the location of your screen, is shifted by an amount proportional to the magnetic flux. So from an experimental point of view, what you would find is that depending on the amount of magnetic field you put in here, you'll shift the interference fringes. It's as if they're displaced by some amount Q times the magnetic flux there. So you can actually, by tuning the magnetic field, you can shift the interference fringes around, and you can, observe that just, from measuring where the electrons hit. So that's an amazing consequence of quantum mechanics, that even though this magnetic field is completely isolated, it has infinitely high potential walls, the particle cannot know at all what's going on in there. And yet it does, because of the relative phase shift that you get for particle paths that go, below and above that cylinder. They get a relative phase shift. Now, normally a phase shift, as I said, is not physically measurable. So you can't really tell the difference if a particle goes here, up here, and it's just as it should be, because, this doesn't do anything. A particle can't go in here. It doesn't apply a force, doesn't do anything. But when calculating something like the interference pattern that you get, the relative phase between the different kinds of paths does matter, because in the path integral, we have to add up over all possible paths that the particle can go through. And that contributes to the interference. But, that statement isn't any different from the fact that in two-slit particle, in a two-slit experiment. You also, in some sense, have interference between the particle going through the top and bottom slit, right? That's why you get the interference fringes. It's just now with the path integral, you can kind of calculate that explicitly, right? Because you're literally summing over all the possible classical paths, or over all the paths that the particle can take. So yeah, so hopefully you get a sense of the power, at least the conceptual power of the path integral for quantum mechanics. If you went to recitation, you'll know that actually calculating one by actually integrating over all the paths is very tedious, and you hardly ever do it. But sometimes it helps you understand some nice conceptual things like this Aharonov-Bohm effect, which has actually been observed. It's a real thing. And maybe in next recitation, if there's interest, I can calculate the two-slit thing exactly and sort of put in all the parameters, but I normally just don't do that. The thing I want you to recognize is just this, right? That you have paths on the top and the bottom, and the relative phase difference depends on this magnetic flux. And then the rest of the stuff, the stuff that comes from actually calculating, the phases along those paths on the top and bottom, that I just embodied in these coefficients theta t and theta b. So I just didn't. So a little too tedious to calculate, but we can do that if there's interest later. Any questions about that, Aharonov-Bohm?
I have a question.
Yeah.
So when we're first setting up our propagator, we have the path integrals above and below.
Yes.
When we have the Lagrangian and the integral, what happens to the x dot squared terms?
Yeah, so the full action is the integral dt of 1/2 mx dot squared plus this q x dot a, and this is all inside an exponential. And so what I'm doing is I already did the integral over the x dot squared when I write down this this square root times this phase factor. This is just the integral. This is that part of the exponential. So all of this times all of this stuff is just e to the I over h bar s, and I do the x dot squared part, and I will get this factor times the square root, and that just comes from that free particle calculation we did last time, because I already showed you how to do e to the I over h bar dt 1/2 m x dot squared. This integral, that's just the integrated over all the paths. That just gives you the free particle propagator, which is the square root of the stuff, and then there's also a phase factor, which I just denote e to the I theta. So that's just that part.
Okay, gotcha. That makes a lot more sense.
But yeah, good question. Any more questions? Again, like from the point of view of it's just important to kind of understand the conceptual importance of this, that quantum mechanics can be thought of as a probabilistic description of nature, where the probability amplitudes, which are complex numbers, as we know. You have to take their square magnitudes to get actual probabilities, but the probability amplitudes depend on the sum over all possible classical paths of a particle going from some initial condition to some final condition. And each of those paths is weighted by a phase, and that phase is given by e to the I over h bar times the action along that path, the classical action along that path, which that's just the integral of the Lagrangian. And although an overall phase, right, never matters, the fact that you have all these different paths, all with different phases, and you have to add them all up means that you'll get a bunch of relative phases. And it's those relative phases between paths that's responsible for the actual observable effects. So like another way to think about two-slit interference, right, is they have two particles. You have all these paths coming from the two slits, and they all interfere with each other. And it's that interference between all those different possible paths that's responsible for forming the two-slit interference pattern in the end. And you can analyze that in like doing the semi-classical kind of limit where you say, well, we'll make h bar small, and so most of the paths that contribute won't matter, like all the crazy ones that go off to some crazy far away from the two slits. So the only ones that will matter are just the ones where it's straight lines, right? Like the velocity is constant, just the straight line paths from the two slits to your screen. And so then you only have to worry about the two paths coming from the two different slits, and you can calculate the interference pattern that way. So that would be the path integral way of doing that. So, but that's what the kind of important message is of the path integral. The actual details of calculating it, like actually integrating over all the paths, it's not really so important. Okay, the other thing I wanted to mention is where path integrals are used in other fields. So the path integral is a sort of a powerful way of dealing with a lot of different systems. So it's used in finance, it's used in polymer physics often. And, where it's useful is where you have any kind of ensemble of paths, right? In finance, you would have a stock and it would have some price, right? And the price fluctuates. And you want to know something, on average about it. So a lot of the questions you would ask are things about average properties of such paths. And so in the end, you always want to perform some kind of averaging over those paths. So that leads you naturally to a kind of path integral-y approach. And moreover, we know that the Schrodinger equation, what does this thing do? Remember, the path integral just solves the Schrodinger equation, the time-dependent Schrodinger equation, which it's this thing, and in position space, there's always like some kind of Laplacian, maybe there's some potential. And if you think about what this thing is, this is a partial differential equation, right? There's spatial derivatives and there's a time derivative. And if we take time and we change variables from time to a kind of I times some tau, like an imaginary time, then if we do that, then d dt is equal to d tau d tau dt, which is 1 over I d d tau. If we make this change of variables, then what this equation looks like, right? If you change variables here in time, what you get is you get a single derivative with respect to psi, with respect to tau, and then on the other side, everything sort of remains the same. You'll get, or actually, I guess I want a minus sign. Yeah, it doesn't matter too much, but it's nice to have this be a positive. You'll get some constant here, psi, and then maybe some kind of other, I guess now this has a minus sign. You'll get some kind of equation like this. This is a diffusion type equation. It has a single time derivative and two spatial derivatives. If you have no potential, what this describes is just random Brownian motion. This would correspond to how a probability distribution for a particle evolves over time. If you start the particle at some location x naught, then psi would describe its actual probability distribution at the probability amplitude, and it would just sort of spread over time with its standard deviation or sort of size of that lump growing as the square root of time, square root of tau in this case. So it's the Schrodinger equation via this transformation to an imaginary time is related to a diffusion equation, which describes the sort of random motion of a Brownian particle or a random walker. And so but again, the path integral helps you solve those kinds of equations for like so diffusion type equations. And those kinds of equations describe anything that has any kind of stochastic noise in it, including the stock market. And that's often where these methods are used. So that's the connection. I guess I was going to talk a little bit about one example that I don't know so much about, but I think it's kind of fun, which is from finance. In finance, you have, of course, stocks, and they have some prices. And you can assume that the stock price, its equation of motion, how does it change? Well, it typically grows exponentially with some rate of return, which you would call phi, some constant. This is the rate of return. But then there's a lot of noise, right? There's the stocks. If you look at any stock ticker, it fluctuates a lot. But overall, there's like a positive trend, right? So like if you look at the S&P 500 or something, there's a lot of noise, but overall there's some kind of roughly exponential rise. So in finance, you model the stock price often as what we call a geometric Brownian motion, where so here's one. You have some average exponential rate at which you increase, but then that rate has noise in it. And so overall, you might have some kind of exponential rise in the price, but there's a whole lot of noise around it. And it's geometric noise in the sense that it's multiplicative in the equation of motion. So you have your overall rate of return, and then you have some noise with some magnitude sigma. There's a noise, and this is a random noise. It's like at each time point, it's just a a bunch of, it's a very spiky, noisy function that describes a sort of volatility in the stock price. And that you can think about as a kind of noise in the rate of return. So what's done typically is, this is sort of the underlying stochastic dynamics of the stock market. And then what, hedge funds and people like that do is that they derive various objects like stock options and other kinds of things that depend on these stochastic dynamics, but that take advantage of them in some way. So often you construct some kind of, it's called a financial instrument, like a stock derivative or what have you, and it'll depend on the underlying, as it's called, which is the stock. So it'll be some function of the stock. And then oftentimes what hedge funds want to do is like figure out how this financial instrument, what should be its price? What should we sell this instrument at? And how does it depend on what's going on with the stock price, which is, fluctuating around. So what's interesting is that in these stochastic kind of processes, the chain rule is a little bit different. So if you want to calculate how any function of a random variable like this varies in time, you can't just do like chain rule and like substitute in this equation of motion for the stock price. You have to do a little more work, use something called the Ito calculus to figure out what it is. But roughly speaking, there's the usual chain rule. So it's this plus it's the explicit time dependence plus, the chain rule would tell us that it's df ds times ds dt, and we'll stick in the equation of motion for ds dt. But then there's an extra term, which is comes from the noise. Unsurprisingly, the noise makes the chain rule kind of tricky. And it gives you two derivatives of f with respect to s. So there's an extra term that you normally wouldn't get from the chain rule. And this is how you can use this formula, it's like a chain rule formula, to derive an equation of motion for any kind of financial instrument. So what do we do? A typical kind of thing to do, what is a typical financial instrument? It could be a portfolio. A portfolio that consists of the stock and maybe an option. So a portfolio is, we call it some function pi, and it's going to consist of a stock option, which I'll call big F here. It's called a stock option. Stock option is the option to either buy or sell the stock at some later time. And it depends on the current value, and it depends on kind of the time, because it's a negotiated contract to sell or buy the stock at a particular price. So it's negotiated such that at some time t, big T, say that you by that time you either exercise the option, and you either buy or sell the stock, or you don't, and then the contract kind of expires. So you have something like that. And then often what like hedge funds do is they hedge any kind of position like that, like any stock option, by including in their portfolio some kind of other financial instrument that just moves the opposite direction as what they purchase. So if you like purchase to something that goes up in value, if the stock goes up in value, then you hedge that by buying something that will save you if the stock goes down in value. So there's you can do a hedge where you take the portfolio consists of a stock option plus something that depends on the rate at which the stock option changes with the value of the underlying. And you subtract off that rate times, you buy an amount of stock proportional to that rate of change of F. And that actually allows you to hedge things in such a way that you don't end up losing anything due to volatility in the stock price. And we can see how, because now we can use this mathematics to sort of apply the chain rule and derive an equation of motion for the stock portfolio. So we do this, d pi dt. So now we plug in everything. So this is the derivative of the stock option minus df ds, and this is ds dt, right? We're just taking a time derivative. This depends on time, so you get the full time derivative of this guy does. This is just the slope of that function. It's a partial derivative, so it doesn't, so at a fixed time, how does the price of the stock option change with respect to the value of the stock at some fixed time t? That doesn't change in time. So this is just applying the time derivative, and now we can stick in the equation of motion for the stock price, and that tells us that this is df dt. Then there's plus sigma squared s squared over 2 ds squared. That just comes from this formula here. And now we have to stick in the equation of motion stuff. So we have df ds times the equation of motion, which is phi plus sigma noise multiplied by s. So that's just this first term. That's putting in these three terms from the that's just putting in those three terms from the chain rule, the augmented chain rule that properly takes into account the noise. And then we subtract off the hedge, and the hedge is again the slope times the equation of motion again, which is phi plus sigma noise times s. And you see, lo and behold, these terms cancel. And what you get is that the equation of motion for your portfolio is entirely independent of the noise. It just depends on these terms. It depends on the magnitude of the noise, but it doesn't depend on the noise itself. So the position is hedged in the sense that there's no more uncertainty in it in the time evolution of this portfolio, right? The noise has disappeared. And that means, economically speaking, if this is a risk-free investment, because there's absolutely no noise in it. So the only thing that can happen to it is it can just increase at some rate. And that's typically conjectured to be some quote unquote risk-free rate. And the risk-free rate is typically some small rate that you would get if you invested in something risk-free, like a treasury bond or something like that. If you do that, then of course, this whole thing must be equal to some constant rate of return, which I'll call little r times pi, which is the portfolio value. That's the only thing that it can be. And so that process gives you an equation of motion. Of course, that was deriving an equation of motion for the portfolio. But now that you have shown that it's sort of a risk-free investment, then you know that this must be also equal to this, just a constant rate of return. That actually gives you an equation of motion for the stock option, the F, that instrument that you use to take advantage of changes in the stock price. And if you just look at this, we can plug back in for pi, right? And what do we get? We get that df dt partial here plus a sigma squared s squared over 2 squared f ds squared is equal to r f minus r df ds times s, the stock price. And remember, f is a function of the stock price and the time. and there's some boundary conditions due to the nature of the contract. But look at this. Look at this equation. You have df dt. That's a single time derivative. You have two derivatives with respect to s, and you have one derivative here. But everything else, and this is like a potential because it's something times f. This is just like an imaginary time Schrodinger equation. So you can use a path integral to solve this equation where the path integral in the path integral, s plays the same role as your coordinate and t is still t. And so you integrate over all, in that path integral formulation, you would integrate over all paths that s can take, right, over time. That's like integrating over all possible paths that the stock value can do, you know, from some initial time to some fixed final time. And for those of you who are interested, this is called the Black-Scholes equation, a very famous equation in finance. What is it used for? Hedge funds use it to figure out what price to put on the stock options, and then they sell to like you, the consumer of any stock options, if you want to buy one. That's how they figure out what price they should set it at. They just solve this equation for f, and f gives you the value of that stock option at time t, given the value of the underlying asset, which you can always look up by looking at the stock ticker. So I don't know, for those of you who are not at all interested in finance, maybe that sounds like gibberish to you, but at least I want you to appreciate that in finance, you can get equations that look an awful lot like the Schrodinger equation, where the coordinate here is the stock price. And you can use the path integral to interpret solutions of this equation as sums over all possible paths that a stock can take through time. So that's kind of interesting, and that's why path integrals are kind of conceptually powerful in finance as well. But yeah, that was my one example. Any questions about that? You can actually make it look even more like a Schrodinger equation. You can you can really, it might be weird that this has like an x squared out front. We're not used to that. We're used to having this be a constant, like h bar squared times the second derivative. You can get rid of that by defining, instead of just using s, you can define x is equal to the log of s. And then if you do that variable change, then you really, really get close to a Schrodinger equation. You get df dt is equal to minus sigma squared over 2 partial x squared plus sigma squared over 2 minus r times partial x acting on f. So that's really like a Schrodinger equation, right? This is, you get real close to, plus r, of course, plus r. Yeah. Let me fix that up.